Welcome to the technical lecture from NCTS. Today's subject is aluminum alloys, casting processes and protocols. And we have Mr. Anant Bam with us to enlighten us on the subject. Mr. Bam is a graduate in mechanical engineering and has done his MBA in marketing. After running his own non-ferrous foundry for a decade, he has started consulting since 2007 and has clients in India and abroad. He is regularly conducting training programs for the industry and has presented papers in conferences such as AluCast and Indian Foundry Congress. He is associated with IIT Mumbai and very closely associated with Institute of Indian Foundrymen. I request Mr. Bam to conduct today's session.
Welcome all to this 7th webinar by NCTS IF. Today we will be discussing and comparing various casting processes used in aluminum foundries. A little bit about casting before we begin with the actual presentation of it. Let us understand first whether the component is suitable for casting or not. After going through that briefly, the castability part of it, then we will understand various casting processes. Then depending on the geometry or any other parameter, how to select the right process. We will rush through in a single slide what are the post-casting treatments. And since it was an old presentation, one slide was there which was a costing of castings, which I recently removed while coming here. So let us start directly. Suitability of a component for casting. Casting, as we know, is a physical commodity which undergoes state transformation twice. That is from solid to liquid and liquid to solid. Naturally, there are certain constraints on the component. And those constraints, especially generated out of solidification, they lead to limitations on physical properties. So if we are happy with only size and shape, is it sufficient? And as far as we understand our engineering component, then the answer is no. Since we are making engineering goods, every component requires certain physical and mechanical properties for its design performance. This condition imposes restrictions on design to be suitable for casting process. Roughly, we can categorize them as performance constraints, aesthetic constraints, and constraints coming out of ease of manufacture. During solidification, the grains of every casting are formed. All the physical and mechanical properties are directly proportional to fineness of grains. Too early solidification leads to chilling and delayed solidification leads to mushy structure. Both these cases are not desirable. This means we should have more or less uniform solidification or more or less uniform cross-section of the casting. Thickness adequacy, fluidity. The liquid metal, as advances ahead in the mold cavity, starts losing heat to the mold walls and to the air within. This heat loss makes the viscosity of metal rise progressively. Metal becomes sluggish and eventually stops to move. Since it is inherent property, it forms limitation on the casting wall thickness and span, or the length of the run, how long the metal can flow. Surface tension. Since the cavity of the mold is filled by a liquid, every liquid or every fluid for that matter has got its own surface tension. And naturally, that surface tension prevents itself from adhering to the adjacent surface. So any fine details, lettering, or any aesthetic feature, those things are subject to the surface tension of the fluid or the metal. And hence, surface tension increases, we cannot get a good piece. Drafts and undercuts. As we have to draw the pattern out from the mold, or we have to draw the casting out from the die, naturally it has to have a draft angle. It can be released from the die or the mold. And therefore, we cannot have a right angle or an acute angle to the casting wall. Negative draft causes a dovetail effect and the casting gets stuck into the die. Hence, any such negative draft or an acute angle leads to a loose piece. Every loose piece or an undercut, it leads to a parting line, and hence it affects the aesthetic of the component. Contraction, cracking, and wall thickness. Casting contracts during solidification, it leads to create stresses on its wall. The wall should be sufficiently thick to accommodate these stresses in semi-solid condition or just about solid condition. Alternatively, we may use highly collapsible hollow cores for larger interiors, which may give poor surface finish. Many a times there are ribs or walls which need to be joined to the main body of the casting. Too many junctions at a single point or line create metal inadequacy leading to shrinkages at that portion. Every rib or a web or a wall that itself acts as a radiator fin, and heat is lost from that fin through pin-fin theory, and such heat loss points lead to liquid requirement due to contraction at the center of it or at the junction of it. If the junction is too thin, naturally it fails to feed the liquid and there is shrinkage at the root of such fin. Instead of having multiple junctions at a single point, if one can defer the junction by adequate margin, then naturally such liquid inadequacy can be distributed at multiple places. And hence, we can get rid of this shrinkage problem. Contraction strain. Components like spoke flywheels are prone to such strains. These strains are developed during contraction and act on the junction of the hub to spoke and rim to spoke, leading to cracks at that junction. It can be reduced by odd number of spokes. What happens during odd number of spokes? Two strain components are not added in single line. They are deferred by some certain angle, and hence the spoke itself, it leads to a buckling or bend which is less hazardous than such contraction strain. Further, such a process can be encouraged by having curved spokes, and such an arc allows more strain to accumulate in it. Lugs, pads, or other projections, they invite turbulence during filling. Also, the section variation at such portions is very high, leading to cracks and shrinkages. It's better to avoid any such section variation, although it is required by design, but then we have to go for selective cooling of such pads so as to achieve uniform solidification. It can be further assisted by providing proper fillets. Now, this is a silly slide, you may say, but I have witnessed many such designs and drawings wherein the designer has got certain thing in his mind, but the drawing reflects something else. In a tapping boss or in a clamping hole boss, if the tapping is required for M10, the boss diameter itself is 8 mm. And we cannot have such a large hole drilled in such a boss. It's a silly mistake, but it happens. So such design mistakes have to be avoided, and one has to ensure sufficient wall thickness even after machining. Too small cores can be avoided. And as a thumb rule, then one can say that anything smaller than ½ inch, it can be avoided very easily. In case of aluminum castings, when we talk of permanent mold or die casting, then we can go as small as 4 mm or 5 mm cores using metallic pins or metallic inserts. But anything smaller than that for aluminum, it has to be avoided. Too much machining allowance, it has to be avoided because any swollen casting, it adds to the mass of the, and nowadays parties are asking for per piece basis. Lighter the casting, more is the benefit to the foundries. Also, metallurgically, the skin of casting is the earliest solidified portion, and hence it has got best metallurgical properties, mechanical properties, and we are removing that by machining. We should go for the smallest or minimum possible machining allowance. Practically for HPDC castings, 0.5 mm on tool point is good enough. 1 mm for medium size castings, gravity die casted, And 3 mm on tool point is sufficient for very large castings, more than a meter or so through sand casting route. Fillets and radii. They not only eliminate the risk of shrinkage, but also add to the aesthetic value of the component. Any sharp curve or any sharp bend, it hits an eye and it is not suitable for soft value addition. So all curves and bends, they restrict the cracks and the component looks good by such curvy nature. Instead of having a simple Z-type bend, we can have a multi-axial single bend, thereby reducing chances of any further hindered contraction. Such logic works very well for tubes and pipes. Usually, aluminum components are used in engines or intake manifolds or air pipes or anything like that. And thereby, you have to connect one end to the other end. Both the ends are fixed geometrically. So best way is to design something like a rubber hose fitted to one end to other end. And the natural catenary or free fall curve which that rubber hose will attain, that one has to follow during the design of aluminum component. That leads to least possible stresses during casting, the easiest metal flow, and casting becomes good. Aesthetics, surface finish criteria, these things have to be noted earlier to process selection. High pressure molding or die casting, they lead to a better surface finish. But again, all those processes have got limitations of its own. And one has to understand the process and the quality requirements and mix and match both to deliver a good casting or a good sellable component. Ease of operation. For foundrymen as well as machining and assembly shop worker, it must be considered, because if you are talking of mass production of anything and everything, time study has to be considered. And during time study, if you find that fitting some component on a jig, or maybe opening some die, operating some loose piece, placement of core, all these things, which are non-value added items, although essential in the process, they do not add to the value of the process. So all these things, they lead to increase of time, thereby increase of the cost. So have sufficient reference planes, provide clamping pads, use minimum machining, standardized fitments and size to limit the tooling, make maximum operations in single clamping, make simple assemblies. All these things are applicable to the machining and assembly, but they have to be considered during design stage itself. Now let us understand the core subject, the various casting processes suitable for aluminum alloys. They can be listed as sand casting, gravity die casting, low pressure die casting, high pressure die casting, and the fifth category, which is a broader category, other casting processes, which may include centrifugal casting, investment, that is lost wax, lost foam, or any other casting process. It's a primitive form of sand casting, loose pattern, hand molding. But you may say that Aligarh, Muradabad, as well as certain pockets making some handicrafts, all jobbing foundries. Even in Chakan, Aurangabad, Pune, all these areas also, they still follow this primitive practice. There are only one or two foundries in India which have machine molding for aluminum castings. Why is it so? Because aluminum being very friendly to permanent mold casting, is die casting, hence only prototype or small batches they are remaining with sand casting. And hence sand casting is not popularly made in any automated molding line. In sand castings, mold is made by sand bender system using a pattern and a molding box. Such molds are temporary, and for every casting, one mold is necessary. Molds can be made by hand molding or by machine molding. However, for aluminum castings, machine molding is not popular in India. The process is having many variables and prone to more defects. Also, the surface finish is quite rough. However, this is the fastest route for any casting development for a small batch. The capital input costs are least, but variable cost is slightly high. The dimensional repeatability is poor, and hence larger machining allowances are necessary. Herein you can see that the die is being sprayed with die coat. That's the die preparation part of it. Now sand cores are being placed in the same die. You can place multiple cores along with metallic inserts. In gravity die casting, the mold is permanent. It is made of metallic die. Since the metal fills the mold under gravitational force alone, it is called gravity die casting or GDC. The process can be automated to a great extent and repeatability is excellent. Surface finish is superior and strength is maximum. Capital input is slightly higher and hence process demands moderate or higher volumes. Sand cores can be placed for hollow interiors and the casting can easily be heat treated. The die operating mechanism becomes an issue for larger castings. But nowadays, with advent of larger hydraulic power packs and larger hydraulic pumps, size of casting has not remained any limitation on gravity die casting process. The further advancement in it is tilting gravity process or Derville process. The metal is poured in a saucer attached to the die and the whole assembly is tilted so that metal fills in a laminar flow. This delivers better mechanical properties and issues related to filling are minimized. You can control the tilting speed and fill rate both, thereby adjusting directional solidification required for the component. In tilting gravity or Derville process, the mold is tilted along with the pouring basin or the saucer. This eliminates turbulence and one can achieve directional solidification with maximum yield. The process can adopt direct top pouring and the castings made are superior in mechanical properties and overall quality. The equipment is slightly expensive, but due to excellent results, this method is commonly used for critical castings like cylinder heads. Sand cores can be placed, heat treatment is very easily possible. I have seen many foundries producing cylinder heads for Indian as well as foreign cars. And the heads produced by this tilting gravity process are far superior than any other process. I have seen all three processes for cylinder head manufacturing, that is stationary gravity process, tilting gravity process, as well as low pressure gravity process. But the performance of tilting gravity cast cylinder heads is the best. Next is low pressure die casting, wherein die along with operating mechanism is mounted on the top of the furnace itself. A stop tube or a leak-proof tube connected to the die bottom is immersed in the crucible. The furnace, crucible and bottom of the die, everything is in a pressure-tight chamber. Once the die is closed, the bottom chamber is pressurized by means of inert gas or by air. That pressure delivers direct pressure on the surface of molten metal within the crucible, thereby creating a fountain of metal through the stock tube. That fountain enters the die from the bottom. It spreads throughout the die. Since die is also blue mashed, it doesn't leak through the die. And once fully filled, a back pressure is sensed. Once that back pressure is sensed, a holding pressure is applied. A solidification time, the estimated solidification time is calculated for that much time the holding pressure is applied. Then the pressure is released, thereby allowing the excess metal within the stock tube to fall back into the crucible, and then the die is open, component is ejected. You can read the same thing in the slide. In LPDC, the die is similar to that of GDC, but it is closely matching and airtight. Such die is mounted on top of the furnace and the pouring point is at the bottom of the mounting plate, which is connected to a metal pool by means of a ceramic or metallic tube, which is called as stock tube or riser tube. Compressed air or inert gas is then pushed into the furnace. Here in one point I forgot to write, that is the furnace and the bottom of the die or the bottom of the mounting plate. All these put together make a airtight or pressure tight chamber. And we are putting compressed air or inert gas into that airtight chamber. which develops pressure on the liquid metal, thus pushing it upwards through the stock tube and filling the mold from bottom till top. Pressure is released only after complete solidification, and liquid metal in the stock tube drops back in the furnace, thus giving us a solid casting with maximum yield. Sand cores can be placed and the casting can be heat treated. There is one drawback in it, that we have to consider 1 or 2 pouring points maximum. Since the crucible mouth is the limitation on how many pouring points or how many stock tubes one can place, you can have maximum 2 pouring points, that is 2 stock tubes. And thereby, any other section variation which is away from these pouring points, you have to cater it by way of side feeders or by way of accelerated chilling through heat pipes or any other such condition. So if you have a component like a box having too many mounting pads on its rim, then you will encounter shrinkage at all those mounting pads. This process is very, very popular for alloy wheels or automotive aluminum wheels, because the wheel rim does not have any isolated heavy section. The heaviest section of the wheel rim is the hub of the wheel, which can directly be connected to the stock tube, wherein the filling point is created. And since the rim thickness is more or less uniform, it does not require any ring riser, and solidification is easily achieved, and productivity is increased, yield is increased. You can get as much as 90 to 95% yield for any alloy wheel. Pressure die casting. Herein, you can push the aluminum metal just like injection molding. Metal is poured into the cylinder, a piston pushes it, the metal is filled into the die, and after solidification, it is ejected. In case of pressure die casting, metal is injected into a pressure tight die by pneumatic force very rapidly. Since the pressure is very high, equally strong clamping force is needed. Rather, it is not equally strong, it has to be 1.25 times larger than the injection force. It is needed to keep the die closed, otherwise a flash will appear. Very thin walled castings can easily be made by this route. Since the capital input cost is very high, this route is suitable for high volumes only. The dimensional stability is excellent and machining allowance can be kept at minimum, say 0.2 to 0.5 mm on tool point. Due to extreme turbulence in mold filling, the castings often have inclusions and tiny porosity, which is compressed minutely. Such things open up during heat treatment, creating blisters and cracks. Hence, these castings are not heat treatable. The latest advancement in pressure die casting is vacuum assisted pressure die casting or vacuum PDC, wherein the die chamber is evacuated by large vacuum pumps and further pressure die casting stroke is applied, thereby limiting or controlling the turbulence, and hence the chances of any inclusions or any other entity or any cavity being formed and compressed are minimized. Hence, vacuum-assisted pressure die-casted components can be heat-treated. Since metal is strongly pressed against the steel mold at high temperature, there is electron transfer and soldering of aluminum happens with the die. To prevent soldering, HPDC alloys need higher Fe content. Such Fe kills the greed or hunger for Fe, and hence these castings are vulnerable to cracks and microporosities, because higher Fe content leads to microstructural defects. The process can be made highly automated, and hence it is used for many automobile components. The grains are extremely fine, and as such the casting strength is quite high. By such alloy compositions and by such process leading to higher strengths, need of heat treatment is also minimized. In other limitations, sand cores cannot be placed in high pressure die castings. You have to go for metallic pins or inserts, and in some remote cases, salt cores can be placed, which is a costlier process.
Centrifugal die casting process. In this process, metallic molds are rotating.
In case of centrifugal casting, everybody knows that cylindrical shape component can be easily casted, and it is applicable for any liners or rings. I have seen only two foundries producing aluminum castings by centrifugal means, and that's a very, very typical application. Investment casting. In case of investment casting, wax mold or wax free is prepared initially. It is further coated with multiple layers of refractory coatings. After proper drying of these coatings, this particular assembly is first heated to drain off excess wax, and then it is heated in a furnace so as to get a ceramic shell. In such a hot shell, metal is poured, thereby delivering very, very fine surface finish and intricate shapes. One or two slides for the latest process, that is lost foam castings. In case of lost foam casting, expanded polystyrene foam, or what we call as high density thermocol. The replica of casting is made in that thermocol by expanding polystyrene in a die. It is similar to investment casting or lost wax casting. In case of investment casting, we prepare a wax replica. In case of lost foam, we prepare a styrene foam replica. A bunch or tree is made by assembling these replicas by suitable runner, riser, feeding and gating system. This assembly is made by adhesion. We stick these runner, riser, gatings to the replica externally. Then such a bunch is coated, just similar to investment casting. It is coated, but the difference is that for investment casting, you require minimum 4 or 5 coats. For lost wax casting, even a single coat is sufficient. But usually people go for double coating. In replica, after proper drying, it is placed in a mold box, empty mold box. The whole system is vibrated, thereby allowing compaction of the dry silica sand. Only the pouring basin and the exit risers are visible to the surface. Then, in case of lost foam, the metal is directly poured. In case of vacuum-assisted foam casting, the metal is poured with vacuum being applied to the mold. Advancing metal burns the polystyrene, thereby leading to the complete filling of the mold. The volumetric product of this combustion is very, very low. Means if you consider in percentages, the outcome of the combustion is hardly 0.2% by volume of the polystyrene itself. And this often goes along with the metal flow and comes out through the exit riser. In case of vacuum assisted casting, it comes out very easily. You can see an animated video of lost foam casting. This is by courtesy of JK Equipment, Ahmedabad. These blue hoppers are having the polystyrene and its activators, catalyst, etc. It then goes into the doser. Expandable polystyrene glues are created, which are further transferred to the molding machine. In this molding machine, our polystyrene replica is created. Once this is called as a white part, this is the refractory coating. But I found out one lacuna or one incorrect thing in this video, that the refractory coating is applied to usual component. It has to be applied after tree assembly. That is, this total assembly has to be coated. Herein they have shown that the coated component is placed to the coated tree. But actually coating happens to the full assembly. This is the mold box. The tree is placed, sand is poured, it is further vibrated. This sand is totally dry sand. There is no binder in it. Metal poured, it burns the polystyrene. It is as easy as that. Since there is no binder, the knockout and other problems are eliminated. The surface finish is delivered by the die and simultaneously by the first coat of the coating. So sand properties or sand fineness does not affect the surface finish at all. Now, since we have understood the processes, first is wall thickness, then surface finish, then possibility of core work, possibility of heat treatment, and mechanical properties expected. For sand casting, as a thumb rule, for aluminum alloys, minimum 6 mm wall thickness is expected. This I am saying as a thumb rule. It does not mean that thinner castings cannot be cast, but then the economics of the whole situation changes. For maximum wall thickness, there is no limit. Section variation easily adjusted. 5 mm maximum, there is no limit. Section variation can be adjusted, but the degree of difficulty increases slightly. So is the case with low pressure die casting. 3 to 3.5 mm, maximum 25 mm section variation adjustment is still difficult because if you have section variation at the remote area or at the far end, then it cannot be fed because your pouring point is at the center of the casting. For high pressure die casting, minimum wall thickness becomes 1.5 mm, maximum 15 mm, section variation adjustment further difficult. All these are what you can say ballpark figures. These are not hard and fast, but as industry practice, these are considered to be rigid figures. Surface finish. For sand casting, it is the worst surface finish available in the whole system, which is about the best possible can be about 10 microarray. For gravity die casting, the best possible finish is 3.5 microarray. For LPDC, same, because the die manufacturing process or the die surface and the coating surface both put together deliver the surface finish. For high pressure die casting, since the coating is different, it is in liquid form, the mirror polished die can deliver you the mirror polished casting. So the surface finish is excellent in high pressure die casting, which is about 1.5 micron array. Now for both these or other, all these three casting processes, gravity, low pressure die casting and high pressure die casting, why there is difference in the surface finish? For high pressure, it is 1.5 and for gravity and LPDC, it is 3.5 because initially the die manufacturing process and the immediate in contact with the metal is the coating. For LPDC and GDC, the coating is a solid film. The liquid coating is sprayed on the die, allowed to solidify, or the liquid content in it evaporates and thereby leaving a solid particulate matter on the surface of the die. The grain size of this solid matter, which is usually talc or zirconia or alumina or any such refractory material, that grain size and concentration at that location, it delivers the surface finish to the casting. If you have uniform spraying of die coat, then you get uniform surface finish all over, which can be as good as 3.5 micron array. Due to its liquid condition initially, this coating drips gravitically downwards, thereby accumulating at any crevices or any horizontal place which it finds nearest. And such accumulation or such lump formation, it leads to excess deposition of coating, thereby disturbing this finish. So any coating process, it has to be followed very, very carefully. There is a misconception amongst gravity die casters especially that this powder coat, it needs a rough die surface for proper anchoring. But as I said, it is a misconception because the anchoring itself does not happen. It is the sticking of the coating to the surface. And that sticking is through the binder which is embedded in the coating assembly. The coating is a, what you can say, active ingredient, a binder and a carrier, a three-part system. The carrier can be water or a thinner. The binder can be sodium silicate or boron nitrate or any such sticky material. And the active ingredient can be talc, zirconia, silica, alumina, any such material. There are advanced coatings like nanotechnology coatings, wherein the particle size is ground to nanometer. Such coatings are expensive, but they are able to deliver further better surface finish. All these coatings, they wear off because every time metal is being rubbed on it during fill and the solidified castings during ejection, it again rubs on the coating. So the coating part has to be repeated every now and then. Commercial coatings like number 140, number 21, number 39, etc. These coatings are to be touched up after every 3, 4, at the most 5 shots, thereby losing the tandem of the or rhythm of the cycle. Advanced coatings like 1400, 3600 or any further coatings, they are designed to last long. And if properly applied, these coatings can last for as long as 3000, 4000 shots. Every coating has got its own application and its own effect. Since that is not the topic for today's discussion, we will skip it and straight away move to HPDC coatings. HPDC coatings are nothing but lubricants, as they are called. They are either water emulsions of mineral oils or very fine atomized spray of mineral oil. It creates a very, very thin film on the surface of the die. Purpose of this lubricant is binary function. First function is to create a barrier, a physical barrier between the molten metal and the die material, thereby preventing any possible soldering. And the second function is that it has to impart surface finish. The third function of the lubricant or the emulsified lubricant is to provide cooling to the die surface. Since majority of the water in the emulsion is evaporated during spraying itself, and all of it eventually evaporates before die closing, you are left with a thin film of the active ingredient, that is mineral oil or silicon oil. This film keeps on dripping towards the bottom of the die, and usually the ingate is placed at the bottom of the die. So this mineral oil leftover enters the gate part of the system, and the metal stream coming into the die first bombards against this accumulated lubricant and then comes to the cavity, thereby creating inclusions of the lubricant. But however, the surface finish delivered is excellent because it's oily film. There is no solid particle or grain in between the die surface and the metal surface. Core work, every casting or component, it needs some interior portion, interior geometry, for which we place core. For sand casting, any and as many as core work is possible, very easily possible. Similarly, you can place many cores at many locations, but since the mold is metallic, it is not permeable. Hence, core gas, it may become an issue. We have to take care of venting very specifically. So is the case with low pressure die casting. Cores can be placed at multiple locations, but again, due to metallic core gas becomes an issue. You have to assess it carefully. For high pressure die casting, only metallic core pins can be placed. And if you have to place cross pins, that is to the axis of the component, if you want a cross bore, you need a separate extraction mechanism for each and every cross pin. So number of cross pins are limited because the total cycle time gets restricted by operating all these cams or any additional cylinders. Sand casting, all types of heat treatments can be done. Gravity die casting, low pressure die casting, all heat treatments can be done. But for HPDC, castings develop blisters and cracks due to release of compressed contamination. Hence, heat treatment except stress relieving is not possible for normal pressure die casted components. Mechanical properties expected. For sand casting, since the grain size is slightly coarser, you get moderate tensile properties, moderate hardness. Further, it both can be enhanced by heat treatment. For gravity and low pressure die casting, due to the metallic molds, chilling effect is very good. Hence, grain size is controlled towards more fine grains. Hence, tensile properties and hardness in as-cast conditions are higher than sand castings, which are further enhanceable by heat treatment. In case of high pressure die casting, the alloy system itself is different, leading to higher hardness. The process is such that the grain size is super fine, and hence higher tensile and hardness are achievable in as cast condition itself. The grain size or grain structure is very, very fine in case of high pressure die castings. Now we go to the critical part of it, the decision making portion, that is commercial viability. Equipment cost for sand casting, it is very less, because as we have seen, most popularly for aluminum alloys, we go for loose pattern hand molding, and thereby we don't require any molding machine as such. In case of critical components through sand casting route, you go for no-bake molding, which require only an intensive mixer or maybe at the most a continuous mixer. That's all you require for equipment. For gravity die casting, the equipment cost is slightly high. For gravity die casting, the equipment cost is slightly high because you need a die operating mechanism. For low pressure die casting, the equipment cost is further high because you need, apart from the die operating mechanism, you need a pressurized chamber, pressure tight chamber, and which is a large enough chamber to accommodate the whole furnace. For high pressure die casting, it is further high because the equipment is quite sophisticated and on a higher end. Operating cost. For sand castings, the operating costs are moderate due to excessive labor input and sand consumption. In case of green sand molding, the binder is a consumable and replacement cost of the sand after certain iterations is necessary. In case of no-bake sand, it is further high. The reclamation cost is also added to it. For gravity die casting, the operating cost is moderate because sand consumption is minimum except that for core. And the labor cost is also reduced due to mechanized operation of the mold. For LPDC, it is slightly higher because the cycle time, although comparable to gravity die casting, it is always slightly higher than gravity die casting because bottom of the die is placed on the hot furnace and thereby solidification is delayed. Also, to operate this sophisticated machine, you need skilled operators and hence the labor cost is expensive. For high pressure die casting, the operating cost becomes minimum because the machines are so sophisticated, it runs on auto mode and the cycles are so compact that you deliver component in seconds. For a 4 kg component like cylinder block of a two-wheeler motorcycle, the cycle time was as low as 72 seconds. And that's the beauty of high pressure die casting. You don't require any labor here. The metal is poured by auto pour, the die is dressed by auto spraying, the component is extracted and it goes directly to trimming. Commercial viability in case of development time. Sand casting is the fastest route. Because the tooling is less accurate, it can easily be made with advent of 3D printing. You can make smaller patterns or larger patterns by way of multiple pieces of a pattern later on being assembled. So the fastest route is sand casting. Next is gravity die casting, which is moderately high development time due to critical tooling and fixed methading. You have to work more on methading. Then after methading is finalized, you have to carve a tool in a metallic mold. LPDC, it is further high because the quality of tooling, the quality of machining has to be further high. It has to be pressure tight tooling. And again, the fixed methading. And HPDC tooling, the development time is the highest because the tooling is very, very critical. You are injecting liquid metal in the die at a very high force, at a very high pressure, and the die has to be perfectly blue matched. Otherwise, even a hairline gap may lead to whole metal coming out of the die in jet force, leading to fatal accidents. Hence, tooling becomes very critical, and to sustain this force and temperature, the thermal shocks and pressure shocks, the die has to be nitrided, the heat treatment is critical, and thereby adding to the time of development. Minimum batch quantity. Now, you have to strike a balance between feasibility and viability. For sand casting, you can go for as low as one piece. That is in case of any ornamental casting like monuments or any statues. These are popularly made by sand casting and the order quantity is one piece. मुझे भगवान महावीर का एक पुतला चाहिए या शिवाजी महाराज का एक पुतला चाहिए. That's the order quantity. Then you are left with only one choice, that is sand casting. For gravity die casting, you can sustain with maybe tens of pieces or hundreds of pieces. For low pressure die casting, you need slightly higher batch quantity because the loading and unloading time of the die is very high. It usually takes 3 to 4 hours to load one die on LPDC machine, and to unload that die, it requires about 1 to 2 hours. So both put together, you nearly lose one full shift. So minimum batch quantity should be viable to spread over 2-3 shifts. Thereby, this single shift loss due to loading unloading can be accounted for. In case of high pressure die casting, the minimum batch quantity requirement becomes very high because the cycle time is extremely high. Also, the loading unloading time is extremely high. Similar to LPDC, for HPDC also, you lose nearly a shift for loading plus unloading the die. The changeover time, what we call as, is 4 to 6 hours, or it may extend to 8 hours also. And with a productivity of 40 shots per hour, it becomes a requirement that you need thousands of pieces to be produced once the die is loaded. That doesn't mean that you are compelled to or restricted to that quantity. If the party is ready to pay for your downtime, then you can quote for it. If the process is so that the component is feasible only through high pressure die casting, then you should be able to load your one full shift for that single piece which you produce at the end of it. And if the party is agreeable to it, then that's the way out. Now let us summarize all these processes in a single slide. This is the outcome of all the earlier presentation, and I request everybody to read it carefully. And if possible, take a screenshot of it. It will be very handy for all of you. There are parameters which are strength, productivity, finish, core work, quality, leak proofness, minimum wall thickness, consistency, labor input, microstructural properties, capital cost, like that. And the process variables. I need not repeat each and every word. It is self-explanatory. There is one question, common question, which everybody asked me in my every earlier presentation. That is why I said quality of casting is poor in case of high pressure die casting. Because vacuum HPDC is a recent advancement and it is available with only 1 or 2 parties in India. Otherwise, every HPDC casting is a leaking casting. It is very popular for structural pieces, structural elements, but for critical components, you have to go for further compromises. In case of any leak-proof castings, for high pressure die casting, impregnation becomes a process requirement. Usually we consider that impregnation is a salvaging process. But for high pressure die casting, it becomes a process, part and parcel of the process itself. Because all the HPDC components are inherently leaking components. That is why I have put the word poor in front of quality. In this last slide, we can briskly touch upon all the post-casting treatments possible. First is mechanical, which is a finishing process. All these. One is lenishing, shot blasting, sand or blast, bead blasting, and vibratory finishing. Electrochemical, which is anodizing or electroplating, and chemical, which is liquid painting or powder coating. All these things are surface treatment processes available. We have discussed about heat treatment and heat treatability in earlier slides, and hence these post-casting treatments are preparing the component for assembly, converting a machine component or maybe a casting from a casting to an subcomponent of the assembly. So that's the end of my presentation.
Thank you, Mr. Bam, for the lecture, giving all the details about the various processes used for producing aluminum castings, the important process details, practical knowledge for the shop floor working was of great interest. Thank you for the lecture.